chapter, actually the new half of the course, the second half of the course, chapter 08, Mandelbrot. We passed chapter 7. Do you remember? It was really quick. Okay, we start with Mandelbrot set. Who is hearing it for the first time? Very good. Very good, brilliant. Yeah. So, let me duplicate this. So here's what we are going to do. We are going to play a game. So this is a real axis, this is imaginary axis. Okay, we are going to pick up a dot from here. So let's say this is A, this is B. So we are picking up a number, complex number C, which is A plus I times B. So far so good? Then what we do is we say that, let's say Z is equal to C. Okay? And then we start updating Z. This is Z0. Zn plus 1 is equal to Zn squared plus C. Okay? Do you understand this formula? Yes? I mean, we take a number, then add. So basically, the first number, Z0 is this. Z1 is going to be C squared plus C, right? Z2 is going to be C squared plus C squared plus C, etc. Right? So far, any questions? No. Now, here's how we get the Mandelbrot set. If Zn diverges or let me write it like this. As n goes to infinity, if Zn does not diverge, let's call it that way, does not diverge, then it's in the, then C is in Mandelbrot, is in the Mandelbrot set. So, do you understand the question here? Yes or no? Do you have a guess? For example, if I start at 100, C is equal to 100, would it diverge? Let's check. What is C squared? What is 100 squared plus 100? Something, right? What is 100 squared plus 100 squared plus 100? Definitely diverging. So it's definitely not in the Mandelbrot set, right? How about 0? 0 squared plus 0. Is this how we are going to do it? Right? Squared plus 0, squared plus 0. Does it diverge? No. Inside the Mandelbrot set, right? Let me do another. So I'm doing the real numbers because they are easy to do, right? C equals to minus 1. So minus 1 squared plus minus 1. What do you get? Zero. Now 0 squared plus minus 1. What do you get? Minus 1. So you can see that we are back. So it's a period 2 oscillator. Goes back and forth, right? Very nice. So let's write a code. Let's write a
Oscillating is diverging.
oscillating. If it's oscillating, it's not diverging, right? It's oscillating between, yes, finite numbers. It's not minus infinity and plus infinity. Then it's good. Okay? So actually, we can show that once z absolute value is greater than 2, there is no way back. I mean, it will diverge. I mean, you can show this. Okay? How I can show this? I have a picture here, but I don't want to lose time with that. Okay? Let's jump into the code. Very advanced code, right? But we can understand it. So I'm going to use, let me make it 1,000. N is 1,000, and I'm going to span between -2 and 2, 1,000 points, okay, in x direction and in y direction. If you don't understand, just ask right away. So I start with c equals to x plus I times y. And x and y span between -2 and 2. -2 and 2, -2 and 2. Then what do I do? Let me explain these parts later on. But you can see that I'm doing z squared plus c here. And I'm doing some bunch of other things. Let me show what this results in. So I will just 1,000 and 100. Let me just run this code. Boom. You get this wonderful image. Do you see it? So what is this? The black region is the place where you have non-diverging sets. Okay? So let's understand it step by step. Shall we? So now let me explain what this S is. So let me explain it here. So when I start, I have x and y, and these numbers here are c's, right? When I start, I also assign another value s to each cell, and I start with all zeros everywhere, okay? Then I start this procedure of doing, I pick one c and do this z squared plus c stuff to it, okay? Whenever it reaches this z equals to, z absolute value equals to 2, I know that whenever it passes that point, I know that it's not going to come back, okay? So I call it a day. I write that, okay, the s value for that one is whatever the iteration number is. So let's say that point went here, there, and went out. So the value of that point is 5, because it went like first iteration, second, third, fourth, and in fifth iteration it went out. Okay? Yes, okay, that's what I do. But some points never go out, right? So those points will remain at 0. Did it make sense or not? It actually will make sense more if we do it just 2 iterations. Okay, nothing else. I will show you. Boom. I get just this circle. Do you see the... Okay, let me just make the figure smaller. So all these points were already out of that circle, so that's why they are out of that circle, but everything inside remained inside. Just nothing happened to them yet. So let's do more iterations. Okay, these ones went out of that circle in the first iteration. These ones remained in. Okay, these ones were already out in the 0th iteration. Are you with me still? Yes. Let's do 4. Do you remember this one was black before? Now it is white. Because these are the ones that went out in the 3rd iteration. So there was a point here when tick, 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 out. Okay? Once it's out, never comes back. Do you have any questions at this point? No. Now, let's do 10 iterations. And you will see that that middle part shrinks. It gets more and more involved. It gets more and more complex structures around it. Okay? Actually, this boundary is showing us something. This boundary is the following. So the first boundary, the circle, is this. C absolute value equals to 2. That's the first one. Okay? The second boundary is this. C squared plus C absolute value equals to 2. That's the ellipse that you see there. The third one is C, what should we do? C squared plus C squared plus C absolute value equals to 2. Okay? And each time you do this, there are new wiggles that appear on the set, and eventually this set becomes quite involved. Okay? And now, we will do a huge exception here, and we will switch to MATLAB. Yay! To just be able to zoom in. And the reason is I was lazy. What? Yeah, no, this is fine. You see, it's the same code, right? More or less. I didn't explain these absolute value parts yet, but I will explain them. But it's this more or less the same code. Do you agree with that? So if I run this code, okay, I broke the code before, so let me fix it. Okay. Oh, all right. So what we will be able to do with this one is we will be able to zoom in. So I will just choose, for example, 2 points, and it will zoom in and it will calculate. Okay. Each time I choose 2 points, it gets that rectangle and zooms in, like this rectangle. Do you see? Like this set has itself in itself. I mean, if you do it very, very carefully, that thing will appear just like a Mandelbrot set, just like the outside one. Do you see it? A thing of beauty going on forever. Let me go back. Let me show you this medallion over here on the left. There is a mini Mandelbrot set there. Do you see it? I actually zoomed in. Okay, let me show you.
Does it have its own Mandelbrot set?
Its own medallion?
Yeah.
Yes, it does. So, do you see this on the left? There is a small region. Unfortunately, I can't. I mean, this is dark and I can't show where I'm zooming in, but I am zooming in here. Do you see it? You want a medallion. I don't see one. Is it here? Yes, it's there. But of course, if you want to, nice. Does it have a medallion?
Yes.
Yes, it does. And it goes on forever. It has a bunch of interesting stuff going on here, and we can talk about it. It's just mathematics. It's a work of art that has no author. It's brilliant. Very nice. So how about this code? Just quickly, we start with zeros in S and zeros in Z, right? Then this line, what this line is doing, it's finding Z's that haven't blown up yet, and it's applying this formula to only those Z's, because the other Z's are going to blow up and we don't want to deal with floating points. Make sense? Yes?
Yeah.
What is this one doing? This one is telling us that, okay, if it just blew up just now after that operation, and if it was 0 before, that point was 0 before, then set it to n. So after n iterations, it blew up. This gives us, that's what makes this picture has that quality of being like Mordor, Lord of the Rings kind of shine, because the ones that had to go out in the hundredth iteration is actually the closest to the darkness. So you have this glow starting right away after the darkness. Okay? Do you see it? You go from darkness to light, then you fall into this well. Very nice. So far, so good? Yes. And you have MATLAB code with zooming inside your notepad. Okay. Now, do you have any questions? Oh, we will come. We will come to Julia's set after a very long break. Okay, let's talk about periodic cycles here. Oh, yes. I don't have my picture. I forgot to put my picture. I don't know what it has to do with you asking question. Then I remember, but anyways, yes.
What is the purpose of seeing all this zoomed out?
What is the?
What's the purpose of seeing all this zoomed in? Can we use it somewhere?
What is the purpose? Okay. Okay. We will come to the. Well, the first thing is that we have an object that is quite complex, and the purpose will be more and more clear as this chapter progresses. Okay? The whole thing here is, the whole message here, let me give you the message every now and then, is self-reference takes you to beautiful places. Self-reference, when something refers to itself. Okay? But we will understand it more and more. So, no worries. Are you worried? Did you get your answer, by the way? My answer was that you will get your answer later, right? Yes, good. Just enjoy the ride, exactly. So let's understand this a bit further by looking at these periodic cycles. Look. Coming soon. Did it come already? Yeah. Here is our Mandelbrot set. We are really happy to see it again. But we will not zoom. What we will do is, I have this thing here. If I go in, so look at this. If I go here, so what is this? Let me tell you what this is. Wherever I put my mouse, it starts from that C, and it draws like a few steps, maybe 100 steps, okay? So you can see that inside this heart, look at this. If I go closer, it's even more fantastic. Inside this heart, it always converges into one point. Do you see? Like maybe you are not convinced, but what you have here is, I don't want to move my mouse, so it's like A, B, C, D, A, B, C, no, A, B, C, 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 and it falls down. But look what happens if I move to this bulge. Look, look, look. Boom. Did you see that? So what happens is that before it was converging to a single point, in this bulb, it converges in a period 3 cycle. Inside this, you have a period 3 cycle. Same here. Inside this, you have a period 3 cycle. Okay? It depends how you approach it, but you do have that period 3 cycle. Are you happy? How about here? Do you see we still have period 1, but once we move to that bulge, it turns into period 5 cycle.
Actually, if you move horizontally, it will be all that.
Horizontally?
Like, I mean, just go to the small part now. You will see all of them because it's like bifurcation diagonal.
Yeah. Look, here I have period 1 still. Like what happens is that tick, 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 like this. But then once I move to this, that tick, tick becomes, I mean, it doesn't converge to 1 point, but 2 points, A, B, A, B, A, B. What do you think will happen when I go here? 4, and then 8, etc. Okay? Yes.
What are the mouse points? Like,
What are the, what is the,
by the pointer, like mouse pointer, is this the starting point?
it's the starting point, z equals to c. It's not only the starting point, but it's also the parameter of the equation. It's z squared plus c, right? It corresponds to that c. But it's also z equals to c. It's also the starting point, also the parameter of this z squared plus c. So we are actually plotting an equation that is, I mean, you take the equation, put the output as input. We are plotting the parameter space where it doesn't blow up. So this dark region is the parameter space where it doesn't go to infinity. That procedure for that parameter doesn't go to infinity.
Why does it have like more than one branch? If it's like just the equation, shouldn't it be a single branch?
You are thinking that this is the starting point, but then it goes to here. Okay, if I move it, I can't show with the mouse. Okay, let me do this. So you start here, then you move 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 here, and you converge here. But once you are over here, when you start from there, then it's like A, B, C, A, B, C, A, B, C. Like if you go there, do you see? If I, okay, let me do another one of
What
these.
about medallion?
Let me talk about medallion. Coming soon. Do you see? A, B, C, A, B, C, A, B, C.
It's like just repeating.
Repeating. Not convergent to a single point, but it's also not diverging. That's the point. Hmm? What is alternating? Yes, but it's not going into infinity. Probably there are like huge, for example, this one is probably what, 8? By the way, if it's 3, it has an antenna that has 3 branches. Do you see that? If it's 5, it has an antenna that has 5 branches there. I don't know if you can see. How about the medallion? What's happening with the medallion? What's happening with the medallion is this. Do you see how when I go here, it's like just breaking into 2?
Yeah.
So the medallion is actually period 3. It's the period 3 window that we will later see in something else. I don't want to spoil the surprise. But you see 2 points, right? The third point is outside the range. Okay? So imagine you have period 3 in that medallion, but as you move around, that period 3 goes to period 6. So it's just like the bifurcation, the one thing becoming 2, but you don't start from 1. Here you start from 1 and it bifurcates to 2, right? Here you start from 3 and it bifurcates to 6. I hope it makes sense. That's how you get a full copy of the Mandelbrot set, because it's just the same thing, but you start with 3 branches at the beginning. All right. We are, yes.
What happens when we touch some of these yellow and red points? At the boundary?
I mean, we go to infinity if we are not really careful. Look, this is 5, but around it, that 5, for example, probably we are touching the place where it goes from 5 to 20. Do you see from 5 to 20? Because each one is divided into 4 pieces. All right? Very good.
I wish we had zoom with that.
You wish we had. The thing with the zoom is in this one is that it's very slow. Okay, let me think about it. Okay. So let's talk about what's going on here. We need to establish some concepts. So I want to talk about, as you can see, Mandelbrot set has a very intricate coastline. I mean, it's composed of this thing, right? It's very hard to draw a Mandelbrot set.
What's the dimension?
We will come to dimensions, okay? But since you asked, this one goes in and out so intricately that I'm answering your question. The dimension of the coastline is 2. So it's so in and out that the dimension, the fractal dimension, that's what you are asking, right? Hausdorff dimension is 2. But we will come to that. So we need to understand these intricate coastlines, and let me give you this coastline paradox.
More is coastline being infinite, right?
Hmm?
More is coastline being infinite, right?
Yes. Doesn't matter which country. Choose Turkey, right? It's more or less a rectangle. Okay? So, what is the total coastline of Turkey? Anyone who knows it? No? Do you know the area? You know the area. But the length you don't know, and actually it's a good thing that you don't know, because we are going to show a paradox here. So here's the thing. Let's say we go and search What is coastline length of Turkey? 8,000. Okay? 8,000?
8,333.
Yes. How did they find it? They measured it, right? They used some sticks that go around Turkey. And let's say they used 1 kilometer sticks and they found 8,333 of them. So they said the coastline of Turkey is this. But then you wanted to make a better measurement, let's say, and you used half a kilometer stick. What happens with the two of them is that, let me zoom in. Let's say there is such a line which had 1/2 kilometer here, 1/2 kilometer here, okay? But it was going like this. So the 1 kilometer stick actually counted it like that. So it didn't see that intricacy. Once you use it with 1/2 kilometer stick, you will find something longer, right? What about 1/4 kilometer? What about 1 meter? How about asking a person to actually run around Turkey's coastline, going into each one of those intricacies? Okay. How about asking an ant to do that? And how about counting all the atoms that come in and out of Turkey, right? So you can see that what will happen is that the length will go to infinity. So coastline of Turkey is infinite. Coastline of anything is infinite. And we have a paradox there. Okay? So let me draw it. Yes.
Atom has a finite length, so if you go to that,
Very nice.
not paradox anymore.
Exactly. Of course. I mean, we have a political boundary there, right? Like, let's say 1 meter wiggle length there, so it's finite. Yes, absolutely. It's just an example. I will give you a more mathematical, pure example that hasn't politics in it, and you will be convinced further. But if you draw log of the length and log of the stick, this is k, it will go like this. Okay? So as the stick gets smaller and smaller, it will get, did I write it incorrectly? Log of the stick goes to minus infinity, isn't it? Yes, it goes to minus infinity, so it's not 0 here. It can go all the way to minus infinity, right? Log of the stick. So the length goes to infinity. So this is correct. Are you still with me? So what you are saying is that there will be some reasonable value where we stop worrying about the stick size and we will report that value. As easy as that, right? Very good. Let me show you something where you will not be able to get away. Koch curve. So here is how we find it. We start with a triangle. Nice. Then we put smaller triangles on top of it.
Is it kernels or like?
You are right. It's a snowflake. If I draw it like this, it's a curve if we look at only one side of it. So, snowflake. Okay, what happened when I added those triangles? Before, the length of the triangle was, let's say this was 1, 1, 1, and the length of the triangle was 3, right? Once I added the triangles, the coastline increased, right? What is now the new coastline? Let's count it together. This is 1 over 3, right? This is 1 over 3, this is 1 over 3, this is 1 over 3. So in total, it's 4 over 3. There are 3 of them. So we went from 3 to 4. Yes? Now let's add a new layer. What does it do to the total curve? It multiplies it again with 4 over 3. So it's now 16 over 3. Right? And it goes on forever like that. So if you do it forever, just like in the Mandelbrot set you had those intricacies, it will go to infinity. So then we have, and we are sure that it will never go out of this circle, right? So inside a finite area, we have an infinite curve. Okay? All right. Then there are some weird things going on. Basically, bless you. Curves used to be one-dimensional things, and they used to fit inside two-dimensional things as finite things, right? They used to be finite, but now we have an infinite curve that fits inside 2 dimensions. So people started wondering how we can define these shapes, and they came up with a bunch of dimensionality definitions. So one of them is self-similarity dimension. So as you can see, this curve, if you do it very intricately, very intricately, it blurs between 1 dimensions and 2 dimensions, because it's so going in and out that, let me just exaggerate it. Do you see at some point it's very close to 2 dimensions, but now it's very close to 1 dimensions. So something has to be done for definitions there, what's going on here. Okay, so let me do it again. So I have a stick of size A, okay. Then I take 4 copies of this stick, put it like this, A. So I have 4 copies. And the scaling is 3A. Scale is multiplied by 3. Do you agree? So I take one stick, put 4 copies, and made it go 3 times larger. Then let's say, let me just copy this one. Okay, let me erase some stuff here. Let me erase this, let me erase that. All right. Okay, so I take this one, make it smaller. I shouldn't have made it smaller, but it won't fit otherwise. Oops. Do you see? I can do this every time and make 4 copies, and it grows 3 times, right? So self-similarity dimension tells us that the self-similarity dimension, of this object is what?
Not base 3, 4, right?
Yes, like ln 4 over ln 3, or as you said, this corresponds to log 3, 4. But this is how we are going to work with it. Okay, so what is ln 4 over ln 3? It's something between 1 and 2, and as you can see, we have a nice definition, and you can really imagine this. So what happens if the scaling is smaller? Does the dimension increase? Like, we could have taken this and put it like this. Okay? And it's spikier, right? This scaling is lower, so it's less than 3. Do you agree? So the fractal dimension, not fractal, self-similarity dimension is larger than the value previously we wrote. So why it's larger? Because if you continue this, it will actually be spiky and it's going to cover 2D area more fully. I hope this makes sense to you. We can go also to the other extreme and just make this copy like 4 copies of the same thing. Not make it a triangle, but make it like this. Then 4 copies, scaling is 4, ln 4 over ln 4 is
2. Right, 1.
1, right? Which is one dimension. It's one dimensional. No matter how many times you repeat this, it's one dimensional. So it works.
Can I check Hilbert curve?
Why?
Hilbert curve, because its dimension is 2. It's a curve that's like
Is it one of those piano curves? We will come to those. Can we check it? Yes, we can. Because? Its dimension is 2. Was something like this?
Yes.
Let's come. I'm not prepared to do that. Let me give you another. Okay. So all these things, they got a name at some point. It was named fractal. Who named it fractal? Benoit Mandelbrot. Okay. Benoit B. Mandelbrot, where B is Benoit B. Mandelbrot. It's self-referential. Do you understand it? Good. Benoit B. Mandelbrot, Benoit Mandelbrot. Anyways, so Mandelbrot's set, was it actually discovered by Mandelbrot? I don't think so. I think it's named as Mandelbrot set, but by someone who worked on it extensively to honor what Mandelbrot did to this fractal science. So fractals are these structures that has fractional dimensions, and you basically form these fractals by putting together the same things over and over again. Let me give you another example of a fractal. Sierpinski triangle. Here's how you get it. You start with a triangle, you remove the middle part, okay? Then you remove the middle parts of what is remaining. Then you remove the middle parts of what is remaining, etc. Okay? So let's, of course, these parts, let's stop at some level, okay? But just know that they are also intricate inside. Anyways, What is the fractal dimension or self-similarity dimension of this thing?
This log 4 over log 3 or log 3 4 again, I guess.
Log 3 over log 2. Why 2?
Because we double the side length and have
Yeah.
3 same copies.
Yes, we have 3 copies and we scaled by 2. Did you see that? So we have a triangle. If this is the original triangle, and we use 3 of those triangles, but the scale jumps from 1 to 2, not to 3, right? Do you see that? The scale here becomes the scale here. So it doubles. So its fractal dimension is ln3 over ln2. And we have a game that can generate this plot.
Also, can you also explain the definition? I'm confused about one thing. Can I have a fractal that has different fractal dimensions at different points?
Very good question. I think you can. You can just say that here is an object, and you can put one side to be Sierpinski triangle and one side to be Sierpinski carpet. Then it will. But usually, in nature, fractals are generated by one process, and that process results in one fractal dimension. But you can always do those 2 things. Okay, so we can actually let me give you one more thing, and then we can go home. You don't need to be self-similar to be a fractal, okay? Like, for example, let's say I have a box, and I'm going to duplicate this box by putting it in random 3 points. I choose like this, okay? Then I'm going to take that box and put it in random places, like so, maybe. Do you see the difference between the 2? When I copied this one, I copied it up, down, right. When I copied this one, it's up, right, down, for example. Do you see it? I put it in different places. But let's take this one and okay, let's start from the bottom this time and not have a right. Are you following? So the fractal dimension of this one, for example, is going to be, again, ln 3 over ln 2. If you do it many times, it doesn't need to be self-similar. It doesn't need to have its own copies exactly. Can be some weird thing going on, but the fractal dimension will still result. It's a matter of how many copies you have and how much scaling you have. Is it starting to look like a fractal? Yes or no? A little bit. But you can keep doing this. And yeah, exactly. Very good. So we can stop here, but we will continue our exploration in this nice world. Please sign the attendance really quickly. Okay, you can come here and sign.